Hi, welcome to my talk. My name is Ondřej Cífka, and the topic of my thesis is deep learning methods for music style transfer. So I'm doing my PhD at Telecom Paris under the supervision of Gaël Richard and Umut Shimshekli. And I have done my secondment at Interdigital with Alexei Ozerov. So this is the outline of my talk. First, I'll introduce the topic of music style transfer, and then I'll talk about two kinds of music style transfer that I have focused on in my thesis. So these are accompaniment style transfer and audio timbre transfer. And then I'll talk about the topic which is a little bit loosely related to that, which is about positional encodings for transformers and their application to music generation. So let's start with the introduction. So basically, people are transforming existing music all the time. So examples of this practice are variations, cover versions, remixes, improvisation. You have heard yesterday from Furkan that basically any performance of a piece can be thought of as a version of that of the first performance, basically, and somehow adapted to the context in which it's performed. So and the broader goal of this thesis then was to study such transformations and see how we could partially automate them in a data-driven manner. And specifically, the focus was on style transfer. And so I'll tell a bit later something about why we might want to do this. But now let's talk about style transfer. So this is actually inspired by work in computer vision, which you might be familiar with. So in image style transfer, we are given two inputs, the content input and the style input. And the task is to transfer the style between the two. So you can see that the result is depicting the same scenes, has the same composition as the content input, but in the style of the style input, which in this case means it's using the same textures. So now we would like to do the same thing for music. So our inputs and outputs are going to be either audio files or some symbolic music representation like MIDI. But now it becomes a little bit unclear what we are actually trying to do. And this is linked to the fact that the definitions of content and style are not that clear. So content could mean either the full score of a piece. It could mean the harmony, the melody, the lyrics, or some combination of these things. And style could be understood as composition style, arrangement style, performance style. It could even mean instrumentation or timbre. These things can be part of style. So in each of these things will give us a bit of a different flavor of the style transfer task. So why are we interested in this task and what are the possible applications? So first of all, the obvious, I think, application is cover song generation. So this could allow us to generate automatically a cover of a song in the style of a different song. So the result would be kind of a mashup between the two. And this could be a very entertaining application for end users. Maybe you could imagine trying to revive an artist who is no longer alive or something like that. But maybe even more interesting is that style transfer could be applied for creating tools for musicians to experiment with different styles in a quick, efficient way and incorporate them into their work. And one nice example is timbre transfer, which could be used even to create audio-controlled virtual instruments if you were able to do it in real time. So you can imagine an instrument whose parameters are somehow controlled by some audio signal. And finally, we hope that work done on style transfer, music style transfer, can be in the future extended to some transformations with cross-model conditioning, for example, to adapt some piece to the content of video or the situation in a video game or specific mood. So you can imagine, instead of, as in the last talk, generating playlists for a given situation, you could adapt the music itself to that situation. So their main contributions are as follows. So unlike much recent or prior work, which has focused on translation between a fixed set of musical styles, we focus more on music style transfer, or as we sometimes call it for clarity, one-shot music style transfer, which is, well, as we have defined it. And so first we propose a novel approach to accompaniment style transfer based on supervised sequence-to-sequence learning from synthetic data. And then also an approach to audio timbre transfer, which is based on self-supervised learning and discrete representation learning. And for both of these tasks, we also propose evaluation protocols, which are sort of the first comprehensive protocol composed of automatic metrics for music style transfer. And then topic which is a bit separate is that we studied positional encodings for music generation and continuation, and we proposed so-called stochastic positional encoding, which is a form of relative positional encoding for linear complexity transformers. So I will have to simplify a lot to cover all of this. So let's dive into the first topic. Yeah, so I wanted to mention that all the contributions have companion websites and blog posts. The one interactive demo, and we are also have released all of our source code, and where possible, we have also released the data. So let's talk about accompaniment style transfer. So this is work that is spread over two publications, one in ISMIR and one in IEEE Transactions on Audio, Speech and Language Processing. And so the second paper sort of builds on the first one. I will mostly focus on the second one here. So the focus is on accompaniments in popular music and jazz, and the task precisely is to generate a new accompaniment for one piece in the style of another. And we are working with symbolic representations, specifically MIDI. And to be precise, we define content as the harmonic structure of a piece, which can be represented as a chord chart, which you can see right here. And the style is defined simply as the accompaniment style, which the rhythm section of the band would use when accompanying based on this chord chart. And so here is an example. We are given two pieces as input. They have different chord sequences, different styles, and then we want to combine the harmony of the first piece with the style of the second without having access to an explicit representation of this information, right? So we are not given the chord chart, we're not given any style labels. All we have is the MIDI file, so all we know all about which notes are present in the piece, and then we have to work with that and generate another MIDI file. And we want to do this in a data-driven way. And since there is no existing parallel data set or aligned data set of music, this means that we cannot directly use supervised learning. So we would have to use, what we could do is either use unsupervised learning methods or generate synthetic accompaniments. And this is what we chose to do here. So we use accompaniment generation software called Band in a Box to create a parallel data set of accompaniments in many different styles. And then we use it for supervised training of sequence-to-sequence models. And then we can leverage their power, which has been demonstrated on machine translation. So here is a diagram of how this works. So we start with some chord charts, which here are denoted A and B. And so we take A and generate accompaniments for it in two styles, S and T, where S is the source style, T is the target style, and these then serve as the content input and the prediction target, respectively, for our neural network. Then we also have this chord chart B, for which we generate an accompaniment of the target style, and that is used as the style input. So you can see this is a completely supervised training scenario. So this is a closer look at the model. So it's based on RNN sequence-to-sequence models, which were designed for machine translation. But here we have two encoders, one for the content input, one for the style input, and then a decoder that, based on the representations computed by these encoders, generates an output sequence, which is a token-based representation of the music. A large part of our contribution is also our evaluation protocol. So here we want to consider basically two criteria: content preservation, which is how well the output preserves the harmony of the content input, and style fit, which is how well the style is transferred from the style input. How well do we fit the target style? And the idea of the metrics is that to compute similarities between the result and the respective inputs. So content preservation is computed as a similarity of the pitch content, while style fit is computed as similarity of so-called style profiles, which is a representation of style that we propose, which is based on some statistics of musical events. So I will not show any concrete results, but I will say that we found this approach to be an effective approach for accompaniment style transfer, and we have shown this using our novel set of music style transfer metrics. And we also observed that the approach can generalize the styles unseen during training. And in our paper, we also include other experiments that are aimed at understanding the style representation that was learned by our model. There is a website that accompanies this paper, which contains an interactive demo, and we also release the code and the generated data set. Now let's move on to audio timbre transfer. So this is work that has been published in ICASP this year, and here we work with audio. So we're given two audio recordings, each of a single musical instrument, and so in this example we have this trumpet playing a specific melody and a guitar playing a different melody, and then what we want to do is combine the melody of the trumpet with the timbre of the guitar, and this without any explicit representation of these features, just given the audio. So the method that we proposed is based on VQVA. So let me introduce the VQVA. So this is the vector quantized variational autoencoder. So it's an autoencoder with a discrete latent representation. So that means the encoder outputs a sequence of vectors which are quantized using a learned codebook. And this representation has a limited representation capacity, which is referred to as the discretization bottleneck. And so this has been exploited by the original authors of VQVA to do speaker conversion, where they found that simply by using this discrete representation and then by feeding in the speaker ID into the decoder, they were able to, well, basically remove the speaker information from the latent representation, and then by feeding it in again, they were able to do speaker conversion. And in this work, we use a similar approach to achieve timbre transfer. So this is what our model looks like. So it is a VQVA with an additional style encoder. So it looks a bit similar to the model I presented earlier, in that it has a content encoder and a style encoder. But now the content encoder together with the decoder form VQVA. And the idea is here that we would like to train this in a self-supervised way. We don't want to assume that we have aligned data, so we cannot do supervised learning. So this is how it is trained, and it rests on three key points. The first one is that we have a discrete representation of content, right? So the content encoder and the decoder basically are trained as a VQVAE to reconstruct the input with this discrete representation in between. And on the other hand, we choose a continuous representation of style, which is produced by the style encoder and then fed into the decoder. And the idea here is that by doing this, we are basically encouraging the content encoder to remove the style from the representation. And finally, we need to ensure that actually the style encoder is going to encode style information and not content information. And to encourage this, we use this strategy inspired by self-supervised learning, where basically how we train is we take some audio recordings and we extract segments of them, random segments that we pair up. We call them X and Y. And so, as I said, X goes into the content encoder and then is trained to be reconstructed, while Y goes into the style encoder, and and then it is not reconstructed, but it's just used to help reconstruct text, right? And the idea is that since they are both from the same recording, we can consider them to have the same style, but not necessarily different content. And then, so basically the only information from Y that is helpful for reconstructing X should be the timbre information or the style information. And this is then what should be encoded by the style encoder. And so to summarize, we propose this self-supervised QVAE framework for audio timbre transfer. We were able to show that it outperforms pre-existing methods, again, using some novel evaluation protocol, which is also based on this content preservation and style fit idea. And we note that the proposed framework is largely data-driven, so it could generalize to other modalities, such as symbolic music, images, and text. And there is a website associated with the paper which has audio examples. Now, I want to talk a bit about the last work, which is on positional encodings for transformers, which has been published in ICML. So the motivation for this was that we would like to do symbolic music style transfer on fully multi-track music, where if you, with modeling all the dependencies between the tracks, which is something which we didn't really do in the first work, and then if we want to represent this music as sequences, we get sequences that are very long and which have complex dependencies. So it makes sense to model them with some kind of transformer model. And so what we wanted to do in this work is investigate long sequence generation using the recently proposed linear complexity transformers, and look at extrapolation beyond the training length and the interaction with positional encodings. And so what we propose here is a stochastic positional encoding, which is a form of positional encoding, which is able to capture relative positions while being compatible with linear complexity transformers. And this is done by drawing a connection between positional encodings and cross-covariances of stochastic processes. So I know this is a lot, so let's try to break this up. So, the important part of the transformer architecture is self-attention, which is known for having quadratic space and time complexity. So why is this? Well, here we are given some queries, keys and values, which are basically some sequences of features that enter the attention mechanism. And then what we do is we compute this attention matrix, which is done by multiplying the queries with the keys. So we get a metric matrix which has dimensions n by n, where n is the length of the input sequence. And then we compute the softmax, which here I just draw the exponential part of the softmax, and this is our attention matrix. Right? And we multiply this attention matrix with the values to get the result. So yeah. And then what is done typically is that we add some sort of positional encoding to the input in order to just inform the model about the order of the input tokens. And the typical way to do this is this absolute sinusoidal positional encodings, which basically adds some features that are dependent on position. And this a disadvantage of this approach is that it does not extrapolate well to longer sequences. So when we get the positions that are past the maximum training position, the attention mechanism is not able to attend to those positions anymore. And a way to mitigate this is relative positional encoding, or RPE, where instead of adding those absolute positions to the input, we add some relative positional information directly to the attention matrices. So this information now depends only on the differences between pairs of positions, right? So it encodes some sort of shift invariance. And yeah, the way it's computed is that we compute the attention matrix as usual, and then we add this relative positional information to it. Now, another thing that has been proposed are linear complexity transformers, which aim to alleviate or improve the efficiency of the transformer, right? So, and the idea is that instead of computing this large attention matrix, which has a quadratic complexity, we're going to, we're going to avoid computing it. And so this is done by breaking it down, by decomposing it as the product of some modified query matrix and some modified key matrix, And this then somehow allows us to rearrange the terms and compute this in linear time, right? So this is good news. We can compute attention in linear time, but this is also incompatible with relative positional encoding because we no longer have access to the attention matrix. And in order to use relative positional encoding, we need to have that, right? So I hope this is clear on a high level. So basically, the key idea is that we cannot use RPE together with linear complexity transformers because we don't have access to the attention matrix. And so this is exactly what we are trying to fix in this paper. So we propose stochastic positional encoding, which is a form of relative positional encoding that can be used with linear complexity transformers. On a high level, the way this works is we take our queries and our keys, and we map them to through some stochastic. We map them to some augmented queries and keys in some stochastic way, and then it turns out, and we can prove this theoretically, that when we plug these modified queries and keys into the good old attention mechanism, this is going to induce, on average, some desirable pattern, positional pattern in the attention matrix. And since we can approximate this attention in linear time using linear complexity transformers, we are now able to do RPE in linear time in an approximate way. So I'm not going to go into the details of this, but I'm going to show some results. We have results on music generation and on some non-music tasks. So this is just to give you a taste of the music results. So here we plotted some attention matrices. So basically we trained some performers, which is a kind of linear complexity transformer. We trained it on music generation and on sequences up to length 2040 and 48. And then we generated sequences up to length 3072. Well, it turns out that then the transformer, the performer is not able to attend past the training position. So it cuts off here and this part is not accessible to it anymore. Well, with our proposed SPE, we can attend to the whole sequence length. Well, we can also see this on the validation plot right here. So this is cross entropy by token position. And you can see that as soon as we reach and exceed the training length, the APE loss shoots up sharply, but this is mitigated for SPE. And we can also hear this very clearly on generated music examples that are available on the project website. And I forgot to say that this actually the plots I was showing are the work of our co-authors Shilun Wu and Eric Young. Okay, so I guess I should stop here because I'm out of time. So thank you for your attention.